Um, Bonsoir. My name is Raymond Laflamme. I'm a faculty here at the Institute for Quantum Computing. And welcome all of you to The Entangle, the series of presentations that explore the intersections of quantum information science and technology research and a range of contemporary topics. Many of you who have come to the Institute for Quantum Computing have heard about the goal of the Institute is to harness the properties of quantum mechanics, turn them into tools or technologies that can be useful. But there's more to quantum mechanics than just devices and widgets. There is a profound understanding of the world around us. And this is what we're going to hear about tonight. And we're going to have a wonderful speaker, somebody who appeared recently in BBC Life Scientific, in the Forum of the British Society of Philosophy of Science, talks 2 years ago on the 100th anniversary of Albert Einstein's film equation, appeared at a Royal Institution in the UK, and many more. If I list all of them, then you'll still be here in an hour or two, so I'll stop here and welcome Faye Dowker, Professor of Theoretical Physics at Imperial College. Professor Dowker did her PhD with Stephen Hawking and graduated in 1990 and did a postdoctoral fellowship in Fermilab, University of California, Santa Barbara, Caltech, and then took a position of lecturer at Queen Mary University in London and joined Imperial College in 2003 and became Professor of Theoretical Physics. So join me to welcome Professor Dowker.
Good evening, everyone. I'm going to be presenting an argument to you tonight. I'm going to argue in favour of this claim that I'm making up here, that in our quest to understand the quantum world, we must analyse and question the role of logic in physics. But since I'm going to be presenting an argument, I'm tempted to say logical argument, but it'll be up to you to decide whether it's logical or not. It's important to me that you follow the argument and that you're able at the end to come to a conclusion about whether or not you agree with my claim. And so I invite questions during the talk, so that will help everyone to make sure that you understand the steps that I'm taking in the argument. And so please, if you would like me to clarify something or go over something, repeat something, then please do let me know. And yeah, I would like this to be more of an exchange, an interaction, and something more of a conversation between us than just simply me standing here and talking at you. So before I start my argument, I need to confront directly a reason that some people, and in particular some of my colleagues, might be a little hesitant, wary of questioning the role of logic at all. Because to question logic might suggest that we are going to be illogical, and to be illogical is a bad thing. No one wants to be illogical, and Spock's looking a little nervous there, a little concerned. We don't want to be illogical, but we want to be able to communicate with each other. We want to be able to understand the world and understand each other. What I'm going to mean by logic in my talk is rules for deducing correct statements about the physical world from other correct statements about the physical world. And when you put it that way, clearly that's not something we want to abandon, because that deducing correct statements about the physical world from other correct statements about the physical world, that's an integral part, a major part of science, so we want to get rid of that. What I am going to argue, though, is that we have to abandon a particular set of such rules. And these rules are often referred to as rules of inference. So I will describe for you a set of rules of inference that I claim we must give up if we want to talk about, if we want to get a picture of the quantum world. Now, when I show you these rules, when I tell you what these rules are, you might have difficulty grasping them, even recognizing what they are, recognizing that they are rules of inference. And the reason for that is that we have actually internalized them to such an extent that we don't recognize that we're making these assumptions. And then I'm going to tell you that we must abandon these assumptions. So it's very hard to give something up if you don't know that you give up some assumptions, if you don't know that you're making them. Right? So in the end, I'll be asking you to decide for yourselves whether I've made a convincing case that we should be giving up on these rules of inference. And at the end of my talk, I'm going to present to you a parable. It's called the parable of the quantum pie eater. And your response, the way you feel about that parable, will perhaps help you to decide whether or not you're comfortable with giving up on these rules of inference. That's for later, for the end of my talk. So let's get started. And we'll start with two quantum experiments. The first one is one of the most iconic experiments in all of physics, the so-called double slit experiment. Here's a cartoon of the double slit experiment. And it takes the form of a source of electrons. So that could be a wire that you heat by running a large current through the wire. It gets very hot. The electrons boil off the surface of the wire. And you apply an electric field which accelerates the electrons towards this glass screen. And if an electron hits the screen at a particular point, it causes a flash of light called a scintillation. And let's suppose that our source of electrons is so weak that it's emitting electrons one by one. So one at a time, an electron will pass through this apparatus and hit the screen, cause a little scintillation. And we can make a record of the positions on the screen where the scintillations occur. So we just place a dot on the screen whenever there's a scintillation, and then a pattern of dots will build up over time as more and more electrons go through the apparatus one by one. So between the source and the screen, we place a metal plate that the electrons cannot penetrate. And in the plate, we make two holes in the form of slits, double slit experiment. So the electrons must pass through the slits in order to reach the screen. If they actually hit the metal, then they are absorbed and go through. Okay, so the question is, what is the pattern of dots, the pattern of scintillations that builds up on the screen as the experiment proceeds? So after many, many runs, many electrons, what does the pattern look like? Well, we can ask a simpler question, simpler experiment, which is the single slit experiment. So we block one of the slits. The electrons now have to pass through the single remaining open slit in order to get to the screen. And we do many runs of the experiment, then many electrons through. What does the pattern look like? Well, the pattern looks like this. So the dots are pretty uniformly spread over it would just get thicker and thicker as more and more electrons build up, and they're pretty uniformly spread over the screen. That's what happens to the electron when you have one slit. You can do you can cover the other slit so that it's the opposite, the other slit which is open and the other slit is blocked. And again, the pattern, and run the experiment again, the pattern will look something like this. Okay, so now let's open both slits, let the electrons run through. What does the pattern look like now? The pattern looks like this. So the scintillations form is on the screen where the scintillations occurred, and then empty bands where there are no scintillations, and then a band where the scintillations bunch up, and then no scintillations, scintillations here, no scintillations. You get this striky effect, these bands. And if you think about it, that is very, very odd. So there are positions on the screen, for example, this empty position here, that electrons can get to with one slit open. So they can go through that slit and get to that position on the screen. But if you open the other slit and give them another way to go, they can't get there anymore. They don't go there anymore. So they avoid this position if they've got two ways to go. But if there's only one way for them to go, then they can go there. Okay. So keep that in your mind. And let's look at our second experiment. That's an experiment very closely related to this one, which is an experiment that Martin LaForest does during open days and outreach events here at IQC. So this is something that's here in this building. It's a Mach Zehnder interferometer. And this is a bird's eye view of it. So these are components which are screwed down to taped to a flat tabletop. We're looking down on it. And here is a cartoon of that experiment. So again, this is a bird's eye view of the experiment. We're looking down on top of the table. And the components of the experiment are a single photon source here, which sends a photon in this direction the arrow shows. And that photon, so again, this is a one particle at a time experiment. We're sending one photon at a time through this apparatus. The photon hits this yellow thing, which represents a half-silvered mirror or beam splitter. And the photon can either reflect off the mirror and go down this green path, or go through the mirror and go along this red path. If it goes on the green path, this blue thing here is a mirror, and this blue thing here is a mirror, an ordinary mirror. It will just bounce. It will bounce off this mirror, go along here, and then hit another half-silvered mirror or beam splitter. At which point it can either again go through or reflect. If it goes through, it enters a detector, which I call detector 1. And just for definiteness, let's say we rigged up the detector so that when it detects the photon, it clicks. So if the photon goes through here into detector 1, the detector 1 will make an audible click. And if it reflects off this half-silvered mirror, then it goes down to detector 2 here, and detector 2 will click. And similarly, if the photon has gone through the half-silver mirror and along the red path, it bounces off this mirror up here, ordinary mirror, down here. And again, it has a choice of going down to detector 2 or reflecting and going to detector 1. Okay, so that's the experiment. We can do the same trick that we did before with the double slit experiment, which, remember, was to block one of the slits. So get rid of one of the options that the particle has. So in this case, to get rid of one of the options the particle has, we can block off this green path. So we just put something here to block the photon, to absorb the photon if it goes along the green path. And if we do that, then the experimental results are that 50% of the time, so for roughly half of the runs, the detectors don't fire at all. And that suggests that at this point, at this moment of choice, there's a probability of a half of the photon being reflected and going down here and being blocked, and so it just doesn't reach the detectors at all. And probability of half of it going through the half-silvered mirror along the red path, and then reaching one of the detectors. Okay. In the runs where one of the detectors does fire, if you just consider those runs, so ignore the runs where the detectors don't fire, in other words, the runs where the photon is blocked, half the time, roughly 50% of the time, detector 1 will fire, will click, and half the time detector 2 will click. And that strongly suggests that when the photon makes it through along the red path, when it has a choice here at the half-silver mirror, it has probability half of going through to detector 2, probability half of reflecting off to detector 1. So that the data from this simpler experiment where we block off one of the paths is very suggestive of the path of the photon having a choice 50-50 of going through or being reflected here, going through or being reflected here. Okay, so let's again give our photon the two choices now. So we'll unblock the other path. And what's the experimental data now? Now, the photon can still go along the red path, but now we've given it the green path to go along too. What's the data? We would expect that 50% of the time it would fire detector 1, 50% of the time it would fire detector 2. And that's not what happens. What happens is that detector 2 never triggers. It never clicks. 100% of the time, every single run, the photon will end up in detector 1. It never gets to detector 2. It will only go to detector 1. And again, that's very odd. Something that the photon could do when it only had one way to go, which is reach detector 2, it can no longer do when it has two ways to go. So it has the original way to go, it still has the red path it can go on. But now you give it another option, the green way, it can no longer get to detector 2. Okay. And what is going on? What is going on in the, yes?
Is 1 and 2 arbitrary? Is it sometimes that it'll 100% goes to 2 and 0% goes to 1?
You can set the experiment up so that 100% of the time it goes to 1 and it just never goes to 2.
Okay.
If you fiddle with the experimental details, that you can put what's called a phase shifter, other bits of equipment you can put here, then you can fiddle it so that it only will turn up in detector 2. But in the simple setup that we've got here, it will only ever go to detector 1 and won't go to detector 2. Yeah, good question. Any other questions? Okay, what's going on? What's going on in the double slit experiment? What's going on in the interferometer experiment? And of course, that's exactly the right question, because physics is all about trying to work out what the bleep is going on. And this is a quotation from a spoof Brian Cox video on YouTube. Some of you may know Brian Cox is a British particle physicist who is an excellent communicator of science. He's made many TV series about cosmology and astrophysics and other science. And this spoof, if you look it up, is pretty funny. Actually, this is something that probably the real Brian Cox would also agree with, the sentiment anyway. So physics is all about trying to work out what is going on. What is going on in our interferometer experiment? So I'm going to concentrate on that experiment and not on the double slit. Okay, so here's our interferometer experiment. What are we interested in? We're interested in the firing or not of detector 2. Now, the clicking of detector 2 is an example of an event. It's something that takes place at a specific place and time, and it's something that could happen, and it either does happen or it doesn't happen. So let me say that again. An event is something that can take place at a particular place and time, that it could happen, and when all is said and done, it either has happened or it hasn't happened. So when you do the run of the experiment, beforehand you know that detector 2 could. It's something that could happen. It could trigger. It could click. You do the run, and it either does happen or it doesn't happen. So an event either happens or it doesn't happen. Let me give you another example of event. So event is going to be a very important important concept for my argument. So another example of an event, something that that could happen, that takes place at a specific place and time, is it rains in Waterloo tomorrow between 1 p.m. and 2 p.m. Right? That's an event. And tomorrow evening, we will know. Either it did rain, either that event happened, or it didn't happen. So it's something that could happen, and it will happen, or it won't happen. That's an event. Another event is, example of an event is the Garlic Girls, who are my latest favourite thing. The Garlic Girls will win the gold medal in the women's curling at the Winter Olympics in Pyongyang. That's another something that could happen, and it either will happen or it won't. Now there's an approach, a framework for quantum theory, which is based on this concept of event. And this framework is closely associated with the particle physicist Richard Feynman. And he set out this approach to quantum theory applied to quantum electrodynamics, which is the theory of photons, interacting photons and electrons. And he did that in a series of lectures that he gave, public lectures, that he gave in 1985. And they're collected in a small volume it's just called QED, Quantum Electrodynamics. And it's an excellent book, I thoroughly recommend it. And he describes the physics in terms of events, things that can happen in a particular position in space at a particular time, and will either does happen or doesn't happen. And he also describes the physics in terms of another concept, which is that of history. A history is a particular detailed way in which an event can happen. So, for example, let's consider our event of rain in Waterloo tomorrow. A history, an example of a history is there will be exactly 200,000 raindrops that fall in this specific pattern, and the temperature will be 2 degrees Celsius, and the wind speed will be 5 kilometers per hour. That will be a precise, detailed description of the weather pattern in Waterloo tomorrow, in which it's raining. So it corresponds to the event, but it's a much more detailed thing. It tells you much more than just it's raining. And another history that corresponds to the event of it is raining in Waterloo tomorrow would be, and there's 5,298 raindrops that fall in this particular pattern, and the temperature is such and such, and the wind speed is such and such. So, of course, there are many, many, many histories that correspond to the event of it's raining in Waterloo tomorrow. What about our other event, which is the one of interest for us in our quantum experiment, the detector 2 clicks? Well, for that particular event, there are only 2 histories. The 2 histories are, let me go back to our picture. The 2 histories that correspond to detector 2 clicking are: the photon goes along the red path, goes through the half-silver mirror, ends up in detector 2, and detector 2 clicks. And the other history that corresponds to the event of detector 2 clicking is the photon goes along the green path, reflects off the half-silver mirror, ends detector 2 and detector 2 clicks. So that's a lot simpler. There are only 2 histories that correspond to the event detector 2 clicks. Okay. So event and history. So in Feynman's lectures on QED, he frames the whole understanding of what's going on in terms of these 2 concepts. Feynman explains how quantum theory tells us how to calculate the probability that an event happens. So remember, an event could happen, and after the fact it either has happened or hasn't happened. But before it happens, you'd like to know how likely it is. And Feynman tells us how to calculate the probability of any event. And the rule is the following. You take your event and you find all the histories that correspond to it, all the detailed ways in which that event can happen. Quantum theory assigns to each of those histories a number called the amplitude of that history. There are specific rules that quantum mechanics gives us to find what this number is for each of the histories. You take those numbers for all of the histories that correspond to that event and you add them all up. And then you square it, and that's the probability. Now you may say, well, that's a really bizarre thing. Who ordered that? Okay. And you would be not alone in thinking that. Pretty much everyone who hears these rules for calculating probability for the first time thinks, oh, yeah, that's not the way I would design a theory. If I was starting from scratch and just sketching out how I would make the rules of physics work, that's not what I would think of the first thing. And the second thing you would think of is, well, why is this rule the right rule? And again, you wouldn't be alone in thinking and questioning that and asking that question, why? What we do know is that this works. It works in giving us the correct probabilities of events which are outcomes of experiments, the quantum experiments we would be doing in the lab. So for example, here's our interferometer experiment again. We know that detector 2 never clicks. And this rule will corroborate that. Before we do the experiment, we do this calculation, we'll calculate that the probability of this event of detector 2 clicking is 0. And that's because when you follow the rules, you find that the amplitude of there are two histories that correspond to our event of detector 2 clicking. There's going along the red path and going along the green path. And when you follow the rules, you find that the amplitude of going along the red path is equal and opposite to the amplitude of going along the green path. So they cancel each other. So the sum of these two amplitudes is actually 0. And 0 squared is 0. So the probability of the event is 0. And that agrees with the experimental results. Detector 2 never clicks. Now this framework of events and histories is often called the sum over histories for obvious reason. Because here you're summing over the histories that correspond to the event to give you the probability. And with this framework, with these concepts of history and event, we have everything that we need in order to explore the role of logic in quantum physics. And to do this, to set out these rules of inference, I'm going to use a very useful representation of events and histories, which may be familiar to some of you, but I will explain it. So this representation is in terms of something called Venn diagrams. If you haven't heard of those, I'm going to explain what Venn diagrams are. Okay. So this is a representation of events and histories that correspond to the physical system of weather in Waterloo tomorrow between 1 p.m. and 2 p.m. Each of these red stars represents a history. Now, I've only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are way more than 11 histories, detailed weather patterns for the weather in Waterloo tomorrow. But I've just chosen 11 representative ones. Right? So, but just bear in mind that there are lots of them that I haven't shown. Okay. So here they are. These are weather. Each one corresponds to a detailed weather pattern, detailed description of the weather in Waterloo tomorrow. And this circle represents the event rain. And what that means is that these 5 histories which sit inside that circle, they all, in all of them, it's raining. So each of these has a certain number of raindrops, and more than that, the histories which lie outside the circle don't have rain in them. So these histories correspond to weather patterns in which it's not raining. So every history in which it's raining is in this circle, and every history in which it's not raining is outside the circle. Okay. Here's another event, which is wind. It's windy. And all the histories in which it's windy are inside that circle, and all the histories in which it's not windy are outside. So this one, 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 outside the circle. It's not windy. So this is a Venn diagram. It represents events, which are these regions of the diagram, these circles, and histories, which are these stars which lie inside or outside these regions. Okay, are there any questions about so that will be familiar to some people who have seen this concept of Venn diagram. All right. Now, what about our other physical system, the interferometer experiment? Well, here we again have many fewer histories. There is the event which is detector 1 clicks, and there are 2 histories that correspond to that. That is going on the green path and then going through horizontally here into detector 1. And there's a history which is going on the red path and bouncing off the half-circle mirror going into detector 1. And then there's the event which is detector 2 clicks, and again that corresponds to 2 histories. So the Venn diagram for this case is much simpler. There's 4 histories. This region over here corresponds to detector 1 clicks. That's the event detector 1 clicks. There are only 2 histories in it. So this is going along the red path and detector 1 clicking. This is going along the green path and detector 1 clicking. This event, this region corresponds to detector 2 clicks, that event. And here is going on red path, detector 2 clicks. This is going on green path. That's much simpler, much less going on. Now, this Venn diagram depiction of these events allows us to easily construct new events from the ones we already have. So, for example, the event "it's raining and windy" is perfectly comprehensible, and it corresponds to the region which is the intersection of this circle with that circle. So it's this lozenge-shaped thing, like that. So this is rain and wind. And the histories in that region, in each of those, it's raining and it's windy. Because, let's go back here, this star here, this history, is in the event rain, so it's raining in that history. And it's also in the event wind, so it's windy in that history, so it's rainy and windy for that history. And similarly for that one. And in none of the other histories is it both raining and windy. So it's only in this intersection region that the histories correspond to rain and wind. So this event, rain and wind, is this intersection of the event rain and the event wind. What about if you're interested only in whether it's rainy or windy? Like you've got a bad cold, you don't want to go out if it's raining or it's windy. So in that case, the event corresponds to this region, which is called the union of the event rain and the event wind. So in each of these histories, it's either raining or it's windy. And for any of these histories, you're just not going to go out. So this is a new event, rain or wind, and it corresponds to these histories. So, for example, in these histories out here, it's neither raining nor windy. But in these histories, it's either raining or it's windy. And finally, another event that you can construct from the events we already have is not rain. And not rain is the region of this diagram outside the circle, outside the event rain, because in all of these histories it's not raining. So these histories all correspond to the event, not rain. So this Venn diagram picture gives us a nice representation of events and events that you can construct from the events that you already have. So here's a list of some of the events. There's rain, that will either happen or not happen. Wind, that either happens or doesn't happen. Rain or wind, that either happens or doesn't happen. Rain and wind, that either happens or doesn't happen. Not rain, that either happens or doesn't happen. It's below freezing, that either happens or doesn't happen. It's below freezing and it's windy, that either happens or doesn't happen. You get the picture. Okay? So every single possible event that you can think of for the weather in Waterloo tomorrow will be in this list. Yes?
I missed some
Yeah.
information. So, if the wind and let's say the weather situation based on history, so there must be a periodicity because in the experimental setup you have you show green laser something like that, and there's a periodicity of the wave there. So how can we now compare random history with that periodic situation? Are you talking that?
So there's nothing periodic about the weather.
Yes, there's
Well, apart from seasonal variations, So at the moment, I'm just talking in general about this concept of events. So I'm not specifically referring to the quantum experiment. We'll come on to the quantum experiments. I'll discuss the quantum experiments also, but for the moment, let's just concentrate on this setup, on the weather. Okay, so here I've got a little title statement. In the world, every event either happens or doesn't. Oh yes. Yeah, sorry.
In the rain or wind, you used inclusive, but since you've got a rain and wind, then I would think that the order should be exclusive.
Oh, you can have that as well. So, right, so this is inclusive all.
Yeah.
So,
Or is it exclusive?
oh, that's in the list too. Yeah. So that's another event. So it's somewhere down here in the list. Yeah. Yeah. Are there other questions? Okay, so we can make statements about the world of the following type. The event rain happens. The event wind doesn't happen. The event rain or wind does happen. The event not rain doesn't happen. So all sorts of statements that you can make about the world of that type. And now I'm finally ready to give you an example of a rule of inference. Remember, a rule of inference is a way of deducing correct statements about the world from other correct statements about the world. So a rule of inference is something of the form if statement, then other statement. Okay, so here's the rule. I'm going to show it to you, and if you feel the inclination to laugh, please do so. Okay, here's the rule. Right, here's the rule. If rain or wind happens, then rain happens or wind happens. No one's laughing, but I find that amusing. Okay. Why is it funny? It's funny because it's very hard to see those two statements, rain or wind happens, and rain happens or wind happens, as different. Okay? It just sounds like you said the same thing in two different ways, but really they have the same meaning. That's the way it definitely feels to me when you first hear that. Here's a more general statement where X is just some event. It's one of those events in the list, right? So it could be it's below freezing and it's windy. Right? And Y could be a statement like it's not snowing. Right? So if X or Y happens, then X happens or Y happens. So this is just a special case of this one. That's an example of a rule of inference. Now, why is this not a tautology? Why does this actually have content, meaningful content? How do we see that we're not just saying exactly the same thing in two different ways? How do we see that this is really, it actually means something? It's actually a rule that has content. It's not just circular. And interestingly, it's in thinking about the quantum experiment that we can see that this is not a tautology, that it actually has content. So let's think about our quantum experiment again. So our experiment is this surprising thing that when you send a photon through, it never ends up at detector 2, it always ends up at detector 1. Detector 1 clicks, detector 2 never clicks. So, it's often said that this experiment, these experimental results must be interpreted as telling us that the photon does not go on one or other of these two paths. So you may have heard that commonly said in a quantum experiment. And let me remind you that a phrase that you have probably heard, which is that Schrödinger's cat is not dead or alive, but is in some kind of superposition of the two, or it is both dead and alive, or it is dead in one world and alive in another world, so it's both dead and alive, right? So those sorts of statements you've commonly heard. Okay? So it's often said, so let me repeat this, often said that this experiment tells us that the photon does not go on the green path or the red path. It just doesn't go on a single path. So what does that mean? Well, let's think about our histories and our events for this quantum interferometer. For one run of our interferometer, this region here, remember, is the event detector 1. And we can divide it into two events. One is detector 1 clicks and the photon goes on the red path. The other is detector 1 clicks and the photon goes on the green path. And the event detector 1 clicks is the union of the two. So detector 1 clicks is the event, it goes on the red path and detector 1 clicks, or it goes on the green path and detector 1 clicks. Okay. Let me say that again. The event detector 1 clicks is the event detector 1 clicks and the photon goes on the green path, or detector 1 clicks and the photon goes on the red path. Okay. So it's just another way of saying the event detector 1 clicks. Okay, so remember that rule of inference, that if X or Y happens, then X happens or Y happens. All right, so what does that mean if instead of X or Y we have detector 1 clicks and red path, or detector 1 clicks or green path? Well, that rule of inference becomes, in our case, if detector 1 clicks happens, then the photon goes on the green path and detector one clicks happens, or photon goes on the red path and detector one click happens. But this is exactly what is commonly denied in explanations of, interpretations of this quantum interferometer experiment. Yes?
Is the reason why this statement is not a tautology because there is a case that x and y are dependent on each other. So can we say that it's a tautology if x and y are not dependent on each other?
No, that's not the relevant thing. So, I mean, in this case, x and y are distinct alternatives. So there's no overlap, and they don't. They're not. They're distinct. They're one or the other. Right? They don't. There's no intersection between them. Is there another?
Yes.
Yes.
So I'm wondering if this is a problem with English grammar. So X or Y is not the same thing as detector one clicks, because in the phrase X or Y, you've given an event with two choices, but in detector one clicks, you've given an event with one choice.
Okay. So yeah. So it was just for lack of space that I didn't write. So detector one clicks is the event which is detector one clicks and red path, or detector one clicks and green path.
Okay, so you just shortened it.
I just shortened it.
Okay.
Yeah. So I should have written here detector one clicks and green path, or detector one clicks and red path. So I just shortened it.
Okay.
So Okay. Are there other questions?
You wouldn't have so much trouble if you clarified whether it's an inclusive or exclusive or. If that's an exclusive or,
This is inclusive or.
then
Although in this case it doesn't matter because there's no intersection.
it has to be that, and that cannot be that. Okay? But if it's inclusive, then both can happen.
If it's inclusive, both can happen. That's true.
If you go back to the previous one and look at it either inclusive or exclusive, you'll see that they're different.
So I'm using or here to be inclusive or, but in this particular case, it doesn't matter because there's no intersection. So inclusive and exclusive or are the same in this case. But in general, I'm using or as inclusive or. So let's talk about it after. So this rule of inference is not a tautology because we can conceive of, people have suggested, and we can conceptualize there not being a fact of the matter about which path the photon has travelled. That's something that is conceptually possible for us. So this is not a tautology. It can happen that it can be the case, let me not use the word happen, it can be the case that X or Y happens, but it's not so that X happens or Y happens. So then this rule of inference fails. So it's not a so in that case it fails. So it's not if it can fail, it's not a tautology. Right? Tautology just means you're saying it's circular, you're saying the same thing. But you're not saying the same thing because it can fail. Okay. Now, here are some yes.
Can you give like the non-quantum examples?
I'll tell you about the quantum pi eater later on.
Like the non-quantum examples.
Mhm.
Can you construct?
It's not. It's about pi, so it won't be quantum. It's just the quantum is a joke. So you'll see. You'll see. Non-quantum pi. All right. Here's another collection of rules of inference. Here's the one we've already looked at. If X or Y happens, then X happens or Y happens. Here's another one. If X and Y happens, then X happens and Y happens. Another one. If X happens, then not X doesn't happen. And all sorts of others of this ilk. And together, these seeming tautologies form a set of rules of inference called classical logic. And as I said before, they seem like tautologies. You just have to try extraordinarily hard to see that these are actually different statements. Why is that? Why do we not notice when we're making these assumptions? Why are we able, it seems, most of the time, just to ignore? See, we've got all these inverted commas here to say that this is an event and this is a separate event and that's a separate event. Just ignore the inverted commas. X or Y, you don't have to say, and you don't even have to say, this just is the same statement as that, it seems. So why is that? Why is it very different? I think there was a question. Yeah.
I was mentioning that we just consider them axioms, right? Even in math, when we learn logic, we define all of these three as axioms, and then we build our math on it. So I guess that's what you mentioned. That's the logic.
Right, so if it's an axiom, it can't be a tautology.
Yeah.
So you still have to see them as different.
But if we assume axioms are true, then we can build on top of it.
Right.
That those are tautologies.
Okay, so why do we not notice you making these assumptions? Why do these fields seem very tautology-like? Okay, so here's my explanation. We learn a classical worldview for many different reasons. We taught it in school, we deal with macroscopic objects that behave in a classical way. And in this classical worldview, the world is one history. That's what the classical worldview is. That's classicality, if you like. The world is one history. What does that mean, for example, for our Weather in Waterloo example? So here are our histories. The world is one history. So what actually corresponds to the world, to the weather in Waterloo tomorrow between 1 and 2, is one of these histories. One of them, precisely one. And if that's the case, then all those rules of inference follow from that. So let's do an example. Yeah.
So when you say world is one history, could you also say that every history is an event, meaning that every history either happens or doesn't happen?
Yeah, so it's a sort of minimal kind of event. So yeah, you can consider an event which just corresponds to a single history. That's true. So yeah. Okay, so let's say that let's consider the rule of inference, which is if rain and wind, then rain. If rain and wind happens, then rain happens and wind happens. Okay. So what does that mean? So if rain or wind happens, that means that, and the world is one history. That means that the world must be either that history or that history. If rain and wind happens, it must be in the event rain and wind, which is this one, okay, this lozenge-shaped intersection. Okay, so it's this one or that one. But then those two histories are in the event rain, and so the event rain happens. And the two histories are both in the event wind, and so whichever one of these happens, they're both in wind, so the event wind happens. So because the world is one history, if rain and wind happens, then rain happens and wind happens. Let's consider one of the other ones, which is if rain happens, then not rain doesn't happen. Right? So if rain happens and the world is one history, then the world will correspond to one of these histories in the rain event. But that means that it's not one of these histories which corresponds to not rain. So not rain doesn't happen. And you can go through all the rules of inference, classical rules of inference, that are included in this list of classical logic, and they all hold. They all follow from the assumption that the world is one history. So if the world is one history, then these classical logical rules of inference follow. And it turns out that the converse of that statement is also true. If you can reason classically, if the classical logical rules of inference hold, then the world must be one history. So I'm not going to show you that, but you can do that, you can prove that. So the two things are equivalent to each other. If we can reason classically using these rules, which we kind of internalize and don't even notice that we're making, then the world is a single history. If the world is a single history, then we can reason logically using the classical rules about it. So the classical worldview that the world is a single history is equivalent to classical logic. Okay. So in classical physics, the world is a single history. And the question is, are we forced to give up this view? Does quantum mechanics force us to give up that view? I've already claimed that the interferometer experiment, for example, it leads people to say things like, oh, the particle doesn't follow a single history. It doesn't follow the green path or the red path. But what would go wrong if I said, well, I don't care what people say, I'm just going to say that it follows the red path or the green path. You know, what happens? Does my head explode? What? Are we forced to give up this view? And the answer is yes, we actually are forced to give it up. We have no choice in the matter. We're forced to give up the view. If we keep to this sum over histories framework of events and histories, and if we accept that events of zero probability do not happen. And this little picture here is a sketch of the events. I haven't drawn on the histories as little dots, but so that there are little dots in each. There are actually 8 dots in each of these regions. So this is a sketch of the events and histories in a Venn diagram for a particular quantum experiment, which is a Greenberger-Horn-Zeilinger state for 3 spin-half particles, which are sent through a series of Stern-Gerlach apparatuses, which send the particles into different beams depending on whether they're spin up or spin down in the x and y directions. Okay, so it's something like that. And there are 4 events which have zero probability in this setup. And I've depicted them as 3 of them are these 3 circles, so they have zero probability. If you use the Feynman rule, which is take all the amplitudes of the histories in those events, add them up, and square it, you get 0. 0 probability for this event, 0 probability for this event, 0 probability for this event, and 0 probability for a 4th event, which is the union of the region outside these 3 circles, together with this shape, and that shape. Okay, that's also 0 probability. And if you think about those 4 regions, you see that every single history is in one of those regions. Those regions all together, their union is the whole set of histories. Every history is in one of those events of 0 probability. And so no single one of those histories can happen. The world cannot correspond to one of those histories because which history would it be? Say it was a history here. Well, if that history is the world, this event would happen. But that has 0 probability, so it can't happen. If the history were here, then it's in 2 events of 0 probability, so it can't happen. If it was here, it's in the 4th event of 0 probability, which can't, so it can't happen. So no single history can happen. We cannot, in this experiment, maintain the view that the world is one history. It's just, we cannot. Right, so the world is not one history in quantum theory. Well, what is it then? And the answer is we don't know yet. We are seeking the answer to this question, and we're guided by some principles, some ideas, some rules. One of the rules is that every event either happens or doesn't happen. Second rule is that this is a one-world theory. So there is one world in which every event happens or doesn't happen. And I mention that just because, of course, in questions of the foundations of quantum theory, what's really going on in quantum theory, how do we understand quantum theory, of course, one of the interpretations is the so-called many worlds interpretation. So this is not a many worlds interpretation, it's a one world theory. There's just one world in which every event happens or doesn't happen. Yes, there was a question.
The previous slide with the 0 probabilities,
Yeah.
presumably calculated by the Feynman's rules.
Yeah.
What's the possibility that there's an error in those, and that something that calculates to 0 should in fact have a positive value? Probability.
Good. So I'm assuming that the standard laws of quantum theory are correct. And the Feynman rules in the experiment that I described are actually equivalent to the usual rules of quantum mechanics. So if quantum mechanics is right, then the Feynman, some of the history's rules are right. So I'm absolutely assuming those. I mean, there are alternatives to quantum theory in which the probabilities of events are actually different from those in quantum theory. But I'm not considering that. I'm just assuming that quantum theory is correct, as we know it is correct. And the Feynman, the probabilities that you calculate using the Feynman sum of histories are just the same as the ones you would calculate in ordinary quantum theory. Yes.
How exactly would you differentiate a microscopic world from a macroscopic world? Because I'm assuming it's unrelated, right?
Yes, good question. Yes, in fact, there's no line. I mean, it's a subjective choice. What's macroscopic and what's microscopic? Indeed. So you're reading ahead here. So let me come onto that. So another of the guiding things that we're using to guide us is that events with 0 probability don't happen. Then we'd also like classical logic to be recovered from macroscopic events. We want to be able to reason classically about things like tables and chairs and the wind and the rain. But it would be difficult if we had to conclude that if it's raining and windy, then it's not true that it's raining and it's windy, right? That would be very... ordinary life would kind of run into a halt if we weren't able to make such deductions. So we want classical logic to be recovered from macroscopic events, but we're more flexible about microscopic events. The paths of electrons, the paths of photons, if they're doing funny, things which we can't reason classically, logically about, maybe we're happy with that. But you're absolutely right that the boundary between these two things is subjective. So maybe there's more non-classicality in things that someone might think of as being macroscopic than we might expect. We don't know yet. Okay. We'd also like classical dynamics to be recovered from macro events. That's something that we have to be able to derive from our whatever understanding we gain about the quantum world. Yes?
What does one world theory mean?
It's hard for me to express what I mean by that because I can't understand what a theory that wasn't a one world theory is like. That's the thing. So
Can you tell us what it's not? Is it just from buzzwords? Is it not parallel universes?
right, exactly. It's just not that.
Okay.
Yeah, it's just one world. Right.
Is
And the one world is this world. Right. This world.
And that's separate from the one history.
Right. Yeah, it's one world, but it's
Many
not one
histories.
history. That's right. And the question is,
Yeah.
what is it?
Makes a lot of sense.
Yes.
So these two problems of recovering classical logic for macroscopic events and the other problem of classical dynamics recovering for macro events, are these the same problem in this approach or are they two different problems?
Classical logic, they're two different problems.
Yeah, I mean, because they look like two different problems, but
They are.
if the motivation for introducing a change to classical logic to defining an alternative logic
Yeah.
is to in fact understand what's really going on, then it seems like they should be connected, right? Like there should be sort of are they completely independent?
Oh,
They cannot be completely.
no, they can't. I doubt they're completely independent, but they're a priori they're not the same problem. If you solve this problem, you won't necessarily solve this problem. And the other one. Okay, so I beg your indulgence. I've run over time a little bit. I beg your indulgence to go on a little bit further. I've only got two more things to say. So I promised you the parable of the quantum pi eater. Okay. So remember that a particle like a photon or an electron going through one of our quantum experiments, it can do something if one option is open to it, but once you introduce another option, it changes its mind. It can no longer do that thing. Right? Okay. So here's the parable of the quantum pi. So the quantum pi goes to the pie shop and says, "What pies do you have today?" And the pie shop owner says, "Oh, apple and blueberry." The quantum pi user says, "Oh, I'll take the apple pie." And the pie shop owner says, "Oh, actually, I forgot, there's cherry pie." And the quantum pi user says, "Oh, in that case, I'll have blueberry." Okay. So electrons and photons reason like this. So the joke is that the fact that there's cherry pie available shouldn't influence, or shouldn't have anything to do with whether the quantum pi chooses the apple pie or the blueberry pie. It's irrelevant. There's also cherry. Now, when you tell people, random people, I suggest you try it tomorrow in the street. Okay, tell them this and say, "Do you find that odd?" Right? Most people don't find it odd. It's a very interesting experiment to do. Most people say, "Yeah, I think like that all the time." Okay. So, oops. Maybe there's, we're actually. It turns out that we are more flexible in our thinking than we might think. That we don't apply classical logical rules of inference in our everyday interaction. Maybe we're more quantum, more non-classical than we might think. Yes.
Yeah, because there's content. Because if I pick a certain ice cream, but my girlfriend wants what she wants may influence my decision. So you have interference.
There's content. Yeah. It makes you think about something else, which yeah. Okay. Right. So I want to end with a perspective that I learned from Raphael Sorkin, physicist who's here tonight, who works at Greenwich Institute, which is the following. Great advances in science are often characterized by the fact that they bring into the purview of science something which was previously considered to be fixed and immutable and a background and not actually part of the dynamical laws of nature. So there are many examples. One is the theory of evolution by natural selection. So before that understanding, the species of living things on Earth and their distribution was considered to be fixed and unchanging. But afterwards, we realized that that's just not the case. The species evolve, they die out, they have changed enormously over time, they have their own laws of evolution. So something that had been considered to be fixed, unchanging, was discovered, realized to be itself dynamical, part of science. Another example is general relativity. So before general relativity, the geometry of space and time was considered to be fixed. A fixed background, an arena, fixed, rigid background arena in which physics takes place. But general relativity revealed that the geometry of space-time is not fixed and rigid. It's dynamical. It has its own laws of motion. It bends and warps and ripples, and it's an active participant in our physical world. So geometry became part of physics. So if the lines of inquiry that my colleagues and I are following, trying to use the idea of non-classical logic in understanding the quantum world, if those are right, if that line of inquiry is correct, then quantum theory will join those other great advances in physics in revealing something that we thought of as fixed and rigid to be part of science and have dynamics of its own. And that something would be logic itself. So I'll end there. Thank you very much for listening.